From the moment we open our eyes each morning, the sun dominates our senses. It bathes the world in warmth and light, a constant presence in our sky. We take it for granted, this giant ball of burning gas that hangs in space. But have you ever stopped to consider what the sun truly is? It's more than just a source of light and heat. It's the reason for our very existence. The sun is a star, one of countless billions in the Milky Way galaxy. It may seem like just another bright spot in the night sky, but it holds our solar system together. Its immense gravitational pull keeps Earth and the other planets locked in orbit around it, dictating our seasons, our days, and our years. Without the sun, our planet would be a lifeless, frozen wasteland drifting aimlessly through the cosmos. But the sun's influence extends far beyond simply providing light and warmth. It's a celestial engine, constantly churning and burning, releasing an incredible amount of energy into space. This energy, in the form of light and heat, travels millions of miles to reach our planet, providing the essential ingredients for life to flourish. From the smallest blade of grass to the largest whale in the ocean, all life on Earth owes its existence to the power of the sun. From the moment we open our eyes each morning, the sun dominates our senses. It bathes the world in warmth and light, a constant presence in our sky. We take it for granted, this giant ball of burning gas that hangs in space. But have you ever stopped to consider what the sun truly is? It's more than just a source of light and heat. It's the reason for our very existence. Our ancestors understood the sun's importance long before we had the scientific knowledge to explain it. They built monuments to track its movements, crafted myths and legends about its power, and even worshipped it as a deity. In a sense, they were right to do so. The sun is in many ways the center of our existence. It's the closest star to our planet, a mere 93 million miles away. That may seem like an unfathomable distance, but on the cosmic scale, it's practically next door. It's this proximity that allows the sun to exert such a powerful influence on our planet, shaping everything from our weather patterns to the evolution of life itself. To truly appreciate the sun, we need to understand its sheer scale. It dwarfs our planet in every way imaginable. In fact, you could fit over 1 million Earths inside the sun. If the sun were the size of a basketball, Earth would be a tiny pinhead in comparison. Imagine holding those two objects in your hands. That's the difference in size we're talking about. But the sun is more than just a giant ball of hot gas. It's a dynamic and complex object, constantly changing and evolving. It has a magnetic field, generates solar flares and coronal mass ejections, and goes through cycles of activity. Understanding these processes is crucial not only for scientific curiosity, but also for the future of humanity. The sun's activity can have a direct impact on our planet. Solar flares, for example, can disrupt communication systems and even cause power outages. Understanding the sun's behavior is therefore essential for protecting our technology and ensuring our continued existence. In the grand scheme of the universe, our sun is just one of countless stars scattered throughout the cosmos. Yet for us, it holds a unique significance. It's our star, the one that makes life on Earth possible. In this exploration of the sun, we will delve into the heart of this celestial wonder. We will uncover the secrets of its immense size, its age, and the forces that drive its incredible power. We will journey into its core, where temperatures reach millions of degrees, and explore the mysteries of its dynamic surface. We will also investigate the sun's eventual fate, a glimpse into the far future when this life-giving star will eventually reach the end of its life. This is the story of our sun, a celestial giant that holds the key to our past, present, and future. Join us as we embark on this journey of cosmic discovery. Our sun, a seemingly unique object in our sky, is just one of 200 billion stars in the Milky Way. These stars come in various sizes, colors, and temperatures. Our sun stands out for its size and life-giving light. Imagine Earth as a nickel, the Sun would be a 4.5-foot sphere. That's how much bigger the Sun is compared to Earth. The Sun's diameter spans an incredible 865,000 miles, which is roughly 109 times the diameter of Earth. The Sun's mass accounts for 99.86% of the solar system's total mass. This immense mass gives it the gravitational pull to hold our entire solar system together. Gravity is a fundamental force in the universe, attracting objects with mass toward each other. The more massive an object, the stronger its gravitational pull. The Sun's massive size equates to an immense gravitational force, a force so powerful that it keeps all the planets in our solar system, including Earth, in orbit around it. Imagine a ball being swung around on a string. The string acts like the Sun's gravity, keeping the ball, representing a planet, in a circular path. Similarly, the Sun's gravity acts like an invisible tether, holding the planets in their respective orbits and preventing them from flying off into the vastness of space. This delicate balance between a planet's forward motion and the Sun's gravitational pull is what defines an orbit. It's a cosmic dance that has been going on for billions of years, a testament to the power and influence of our Sun. The Sun's influence extends far beyond the orbits of the planets. Its gravitational pull also affects objects in the Kuiper Belt, a region beyond Neptune that is home to icy bodies and dwarf planets like Pluto. Even further out in the distant Oort cloud, a vast sphere of icy debris that surrounds our solar system, the Sun's gravity still holds sway, albeit much weaker. This vast sphere of influence, stretching trillions of miles from the Sun, highlights the incredible reach of our star. It's a reminder that the Sun is not just an isolated object in space, but the heart of a dynamic and complex system that extends far beyond the planets we know. But the Sun's reach isn't just about gravity. Its light and heat, the energy it constantly emits, also travel vast distances, illuminating and warming our corner of the galaxy. While our Sun is an impressive celestial object, it's important to remember that it's not unique in the grand scheme of the universe. There are stars out there that dwarf our Sun in both size and mass. Some are even millions of times larger. These stellar giants put the Sun's size into perspective, reminding us that we are just a small part of something much, much bigger. Despite its relative smallness in the vast expanse of the cosmos, our Sun is incredibly important to us. It's the source of our energy, the driver of our weather, and the anchor of our little corner of the galaxy. Understanding its size and influence is just the beginning of unraveling the mysteries of this celestial giant that plays such a vital role in our existence. Imagine trying to determine the age of a bonfire you stumble upon in the wilderness. The flames dance and crackle, offering no clear indication of how long they've been burning. Determining the age of the Sun, our own celestial bonfire, might seem like an equally impossible task. After all, we can't exactly travel to its core and extract samples for analysis. But scientists have developed ingenious methods to estimate the Sun's age, piecing together clues from meteorites, the Earth itself, and the Sun's own light. One key to unlocking the Sun's age lies in understanding its life cycle, a process of stellar evolution that unfolds over billions of years. Like all stars, the Sun formed from a collapsing cloud of gas and dust. As this cloud contracted under its own gravity, it began to spin, eventually flattening into a swirling disk of material. At the center of this disk, the densest region, gravity pulled in more and more material, increasing the pressure and temperature until nuclear fusion ignited. This marked the birth of our Sun. By studying the oldest objects in our solar system, scientists can estimate when this momentous event occurred. Meteorites, remnants of the early solar system that have remained relatively unchanged for billions of years, provide valuable clues. These space rocks contain radioactive elements, such as uranium, that decay at a predictable rate. By measuring the ratio of these radioactive elements to their decay products, scientists can determine how long ago these meteorites formed. The oldest meteorites found on Earth date back to approximately 4.56 billion years ago, providing a lower limit for the age of the solar system and, by extension, the Sun itself. Earth itself offers further confirmation. Rocks found in Greenland, some of the oldest on our planet, also date back to around 4.54 billion years ago. This suggests that the Earth, and likely the entire solar system, formed relatively quickly after the ignition of the Sun. But the Sun's own light also reveals secrets about its age. By analyzing the Sun's spectrum, the specific wavelengths of light it emits, scientists can determine its chemical composition. The Sun is primarily composed of hydrogen and helium, the two lightest elements in the universe. Hydrogen is the fuel for the Sun's nuclear fusion, the process that powers our star. Over time, as the Sun continues to fuse hydrogen into helium in its core, its chemical composition slowly changes. By comparing the Sun's current composition to models of stellar evolution, scientists can estimate how long it has been fusing hydrogen. These models, combined with evidence from meteorites and Earth's oldest rocks, converge on an age for the Sun of approximately 4.6 billion years old. To put that into perspective, if we compress the entire history of the universe into a single calendar year, with the Big Bang occurring on January 1st, the Sun wouldn't have ignited until September 1st. Humans wouldn't appear until the last few seconds of December 31st. At 4.6 billion years old, the Sun is considered to be a middle-aged star. It's about halfway through its main sequence lifetime, the longest and most stable phase of a star's life. During this phase, the Sun will continue to fuse hydrogen into helium in its core, providing a steady source of energy for billions of years to come. But the Sun's life, like all stars, is finite. As it continues to burn through its hydrogen fuel, its core will slowly contract and heat up, eventually becoming hot enough to fuse helium into heavier elements. This will cause the Sun to expand significantly, transforming it into a red giant star. When this happens, billions of years from now, the Sun will engulf the inner planets, including Earth, rendering them uninhabitable. While this might seem like a bleak prospect, it's important to remember that we are talking about events that will unfold over timescales far beyond human comprehension. The Sun's age not only tells us about its own history, but also provides insights into the formation of our solar system and the conditions that allowed life to arise on Earth. The fact that the Sun formed relatively early in the universe's history suggests that our solar system is not unique, and that other star systems, perhaps even those hosting life, may have formed around the same time or even earlier. By studying the Sun, we are essentially peering back in time, uncovering clues about the early universe and the processes that led to the formation of stars, planets, and ultimately ourselves. The Sun's light, which bathes our planet in warmth and energy, carries with it the echoes of the distant past, a reminder of the interconnectedness of all things in the cosmos. When we talk about distances on Earth, we use units like miles or kilometers. But when we venture into the vastness of space, these units become woefully inadequate. Imagine measuring the distance between cities in millimeters. It would quickly become cumbersome and impractical. Similarly, using miles or kilometers to express distances in space would result in incredibly large and unwieldy numbers. To tackle these cosmic distances, astronomers use a much larger unit of measurement, the astronomical unit, or AU. 1 AU is the average distance between the Earth and the Sun, approximately 93 million miles. By using the AU, we can express the distances to other planets in our solar system in more manageable terms. For example, Mars is about 1.5 AU from the Sun, while Jupiter sits at a distance of roughly 5.2 AU. The AU provides a convenient yardstick for measuring distances within our solar system, but even this unit falls short when we start talking about the distances between stars or galaxies. Despite its name, a light year doesn't measure time, but rather distance, the distance that light travels in 1 year. Light, the fastest thing in the universe, zips along at an astonishing speed of approximately 186,282 miles per second. To put that into perspective, in just 1 second, light can travel around the Earth over 7 times. Over the course of a year, light covers an incredible distance, about 5.88 trillion miles. This immense distance, 1 light year, becomes the measuring stick for the vast gulfs between stars and galaxies. For example, the nearest star to our Sun, Proxima Centauri, is a little over 4 light years away. This means that the light we see from Proxima Centauri today actually left the star over 4 years ago. When we look up at the night sky, we are essentially looking back in time. Now, back to our Sun. Although 93 million miles might seem like an insurmountable distance, it's important to remember that light doesn't travel instantaneously. It takes approximately 8.3 minutes for light from the Sun to reach Earth. This means that when you look up at the Sun, though you should never look directly at the Sun without proper eye protection, you are seeing it as it was 8.3 minutes ago. The sunlight warming your face right now embarked on its journey across space while you were still finishing your morning coffee. If the Sun were to suddenly disappear, don't worry, it won't happen anytime soon. We wouldn't know about it for a full 8.3 minutes. But sunlight isn't just carrying information about the Sun's past, it's also carrying the energy that sustains life on Earth. The Sun is constantly emitting a torrent of radiation, including visible light, ultraviolet light, and infrared radiation or heat. Only a tiny fraction of this radiation actually reaches Earth, but it's this small fraction that makes all the difference. When sunlight reaches our planet, it interacts with the atmosphere, the oceans, and the land, driving weather patterns, warming the surface, and providing the energy that plants need for photosynthesis. Without the Sun's energy, Earth would be a frozen, lifeless wasteland. This 93 million mile gulf between Earth and the Sun places our planet within a narrow region astronomers call the habitable zone. This zone, also known as the Goldilocks zone, represents the sweet spot around a star where conditions are just right for liquid water to exist on the surface of a planet. Too close to the star and temperatures would be too hot, causing any water to boil away. Too far and temperatures would plummet, locking any water into a permanent freeze. Earth fortunately orbits within this habitable zone, allowing liquid water, the essential ingredient for life as we know it, to thrive. Our planet's distance from the Sun is a crucial factor in our existence, a reminder that we are part of a delicate cosmic ballet. The Sun's story, like that of all stars, begins with a cloud of gas and dust, a nebula drifting through the vastness of space. These nebulas are the birthplaces of stars, cosmic nurseries where gravity slowly draws together the raw materials for stellar creation. Within a nebula, gravity draws together atoms of hydrogen, helium, and trace amounts of heavier elements. As these particles clump together, the cloud begins to collapse under its own weight. This collapse causes the cloud to spin, much like a figure skater pulling in their arms to spin faster. As the cloud spins and contracts, its core heats up, glowing with increasing intensity. This glowing spinning cloud is known as a protostar, a star in its earliest stage of development. Deep within the protostar's core, a critical threshold is reached. The temperature soars to over 10 million degrees Celsius, and the pressure becomes unimaginable. Under these extreme conditions, hydrogen atoms, the simplest and most abundant element in the universe, are forced to fuse together. This process, known as nuclear fusion, is the engine that powers the Sun and all other stars. In essence, it's the process of combining lighter atomic nuclei to form heavier ones, releasing a tremendous amount of energy in the process. When hydrogen atoms fuse in the Sun's core, they form helium, the second lightest element. This fusion process releases an incredible amount of energy in the form of light and heat, which radiates outward from the Sun's core. The moment nuclear fusion ignites in the core, the protostar officially becomes a star. For our Sun, this momentous event occurred roughly 4.6 billion years ago. From that point onward, the Sun entered a long, stable period known as its main sequence. During this phase, which lasts for billions of years, the Sun continues to fuse hydrogen into helium in its core, providing a steady stream of energy that sustains life on Earth. But the Sun's hydrogen supply isn't infinite. Scientists estimate that the Sun has about 5 billion years worth of hydrogen left in its core. Once this hydrogen fuel is exhausted, the Sun will enter a new phase in its life cycle marked by dramatic changes in its size, temperature, and appearance. As the Sun's core runs low on hydrogen, the outward pressure from nuclear fusion will eventually diminish. Without this outward pressure to counteract the inward pull of gravity, the Sun's core will begin to contract and heat up. This heating will cause the Sun's outer layers to expand dramatically, transforming it from a yellow dwarf star into a red giant. As the Sun's core heats up, it will push its outer layers outward, causing the Sun to swell to an enormous size. During its red giant phase, the Sun will expand to engulf the orbits of Mercury, Venus, and possibly even Earth. As the Sun expands, its surface temperature will cool, giving it a reddish hue. Despite this cooling, the Sun's overall luminosity will increase dramatically, scorching the surfaces of any remaining planets in the inner solar system. As a red giant, the Sun won't be fusing hydrogen anymore. Instead, the intense heat and pressure in its core will allow it to fuse helium, the product of its previous fusion reactions, into heavier elements like carbon and oxygen. This helium-burning phase will be short-lived, lasting only a few 100 million years. Eventually, the Sun will exhaust its helium fuel as well. When this happens, the Sun will no longer be able to support itself against the relentless pull of gravity. Its core will contract further, reaching incredibly high densities, while its outer layers will be expelled into space in a beautiful but fleeting display known as a planetary nebula. The Sun's core, now a dense, hot object known as a white dwarf, will slowly cool over billions of years, eventually fading into a cold, dark ember. We often describe the Sun as a giant ball of fire, but that's not entirely accurate. Fire, as we know it, requires oxygen and fuel, and the Sun operates on a completely different principle: nuclear fusion. Imagine a furnace not fueled by wood or coal, but by the very atoms that make up matter itself. The Sun's temperature varies dramatically from its core, where fusion takes place, to its visible surface, and even further out into its extended atmosphere. This temperature gradient drives the flow of energy outward from the Sun's heart, ultimately reaching Earth in the form of light and heat. This journey of energy from the Sun's core to its surface is a fascinating story of its own, involving processes of radiation, convection, and even magnetic fields. At the heart of the Sun lies its core, a region of unimaginable density and temperature. Here, under the crushing pressure of the Sun's own gravity, temperatures soar to over 15 million degrees Celsius. It's within this extreme environment that the magic of nuclear fusion occurs. Hydrogen atoms, squeezed together with incredible force, overcome their natural repulsion and fuse to form helium, releasing a tremendous amount of energy in the process. The energy released from a single fusion reaction is tiny, but the sheer number of these reactions occurring every second in the Sun's core is staggering. Every second, the Sun converts approximately 600 million tons of hydrogen into helium, releasing the energy equivalent of billions of atomic bombs. Surrounding the Sun's core is the radiative zone, a dense region of plasma that extends outward for roughly 70% of the Sun's radius. Within this zone, energy is transported outward primarily through a process called radiative diffusion. In the radiative zone, the high-energy photons produced in the core collide with the densely packed plasma particles, being absorbed and re-emitted countless times. This random walk of photons can take hundreds of thousands of years to traverse the radiative zone. Each interaction with a plasma particle causes the photon to lose some of its energy, gradually decreasing its frequency. Above the radiative zone lies the convective zone, a region where energy is transported outward primarily through convection, a process similar to boiling water. In the convective zone, the temperature gradient is steep enough that plasma near the bottom heats up, becomes less dense and rises, much like bubbles in a pot of boiling water. As this hot plasma rises, it carries energy with it. When it reaches the top of the convective zone, it cools, becomes denser, and sinks back down, only to be heated again and repeat the cycle. This continuous churning motion creates a turbulent environment with giant plumes of plasma rising and falling like waves on a stormy sea. Finally, after a long and arduous journey, the energy produced in the sun's core reaches its visible surface, known as the photosphere. This is the layer of the sun that we see from Earth, a bright, seemingly smooth sphere of light. But the photosphere is anything but smooth. It's a turbulent region marked by granulation, sunspots, and other features that hint at the dynamic processes occurring beneath. The photosphere has a temperature of about 5,500 degrees Celsius, or 10,000 degrees Fahrenheit, much cooler than the sun's interior. It's from this layer that the sun radiates most of its energy into space, including the light and heat that sustain life on Earth. The photosphere is the boundary between the sun's interior and its atmosphere, a region of even more extreme temperatures and phenomena. As we conclude our exploration of the sun, it's important to step back and appreciate the sheer scale and complexity of this celestial wonder. We've delved into its fiery heart, where nuclear fusion unleashes unimaginable power, and traced the arduous journey of energy from the core to the surface. We've explored its vast size, dwarfing our planet and its immense gravity, holding our solar system in a delicate cosmic dance. We've uncovered its ancient origins, a testament to the universe's grand cycle of stellar birth and death. But the sun is more than just a collection of impressive statistics. It's a symphony of interconnected processes, a delicate balance of forces that has persisted for billions of years. Understanding the sun is not just an exercise in scientific curiosity. It's about understanding our place in the cosmos. The sun is our lifeblood, the source of our energy, the driver of our weather, and the anchor of our little corner of the galaxy. Life on Earth, in all its diversity and splendor, is a direct result of the sun's energy. Plants harness sunlight through photosynthesis, converting it into chemical energy that forms the base of the food chain. Animals, in turn, obtain energy by consuming plants or other animals that have consumed plants. The oxygen we breathe is a byproduct of photosynthesis, a gift from the sun's interaction with life on Earth. But the sun's influence extends far beyond providing the energy for life. The sun's heat drives our weather patterns, creating winds, ocean currents, and the water cycle. It shapes our planet's climate, influencing everything from the distribution of deserts and rainforests to the ebb and flow of glaciers. The sun's gravity keeps our planet in a stable orbit, preventing us from drifting off into the cold darkness of interstellar space. This delicate gravitational balance, combined with Earth's atmosphere and magnetic field, creates the conditions necessary for liquid water to exist on our planet's surface, a key ingredient for life as we know it. The sun has been a constant presence in our sky for billions of years, a silent witness to the unfolding of life on Earth. It has watched over the rise and fall of civilizations, the evolution of species, and the transformation of our planet's surface. It has marked the passage of time, its daily and yearly cycles providing the rhythm for life on Earth. From the earliest humans who tracked its movements across the sky to the sophisticated instruments we use today to study its every detail, the sun has captivated our imaginations and inspired our curiosity. It has been the subject of myths and legends, scientific inquiry, and artistic expression. The sun's story is a reminder that we are part of something much larger than ourselves, a cosmic tapestry woven together over billions of years. It's a story that fills us with awe and wonder, urging us to explore the mysteries of the universe and to appreciate our place within it. The sun's influence extends beyond the realm of science. It has been a source of inspiration for artists, poets, and musicians for centuries. Its warmth and light have evoked feelings of joy, hope, and renewal. Its setting and rising have marked the passage of time, reminding us of the cyclical nature of life. Vincent van Gogh, captivated by the sun's brilliance, sought to capture its essence on canvas, his brushstrokes ablaze with vibrant yellows and oranges. Emily Dickinson, in her poetry, pondered the sun's power to illuminate both the physical and metaphorical landscapes of our lives. Music, too, has been deeply influenced by the sun. From Beethoven's Moonlight Sonata to George Harrison's Here Comes the Sun, composers and songwriters have drawn inspiration from the sun's ability to evoke a wide range of emotions, from tranquility and peace to joy and exuberance. As we look to the future, the sun will continue to play a vital role in our lives and in the destiny of our planet. It will continue to provide the energy we need to power our homes, fuel our transportation systems, and sustain our growing population. It will continue to inspire our imaginations, fuel our scientific curiosity, and remind us of our interconnectedness with the cosmos. But the sun's story is not just about the present, it's also about the future. The sun, like all stars, has a finite lifespan. Billions of years from now, it will exhaust its nuclear fuel and enter its death throes, expanding into a red giant and eventually shedding its outer layers, leaving behind a faint white dwarf. Though this eventuality may seem like a distant and somber prospect, it serves as a powerful reminder of the preciousness of life and the importance of cherishing our time on this planet. The sun's legacy will extend far beyond its own lifespan, its energy and influence shaping the cosmos for billions of years to come. And we, as inheritors of its light and warmth, have a responsibility to use our time wisely, to explore, to learn, and to leave our own mark on the universe.